We are about to start our session. Now I will request everyone to please turn off your camera and microphone for better audio and video experience. Hello. Good afternoon, everyone. All the faculty members, and research scholars of different premier institutes. I, Oritra Ghosh, Assistant Professor, Department of Electrical Engineering, welcomes you all in the fourth day session of International FDP on emerging trends on security, sensor, and smart automation system 2020. Now we have two back-to-back sessions today. Our first session speaker is Professor Biswanath Roy from Jadavpur University, Electrical Engineering Department. Without a further ado, I will request Professor Dr. Abhik Mukherjee, Assistant Professor, Department of Electrical Engineering, BBP IMT, to please introduce our honorable speaker. Thank you, ma'am. Now it's up to you.
Thank you, Oritra. Am I audible?
Yes, ma'am. Absolutely.
Okay. A very warm good afternoon to all the wonderful people present here. We are privileged to have renowned Professor Dr. Biswanath Roy as a speaker. I want to share a short biography of Professor Roy. Dr. Biswanath Roy is associated with the Electrical Engineering Department of Jadavpur University since 2000 as a faculty of Illumination Engineering. He completed his PhD in the field of daylighting in 1999 from Jadavpur University under the guidance of late Professor Dr. S.R. Bandyopadhyay after having MSc Tech in Optics and Optoelectronics from the Department of Applied Physics in 1993 and BSc Honours in Physics in 1989, both from the University of Calcutta. He is a Life Fellow of Indian Society of Lighting Engineers, ISLE, a life member of the IEI, the Institution of Engineers, India. I am very happy to share that he was my PhD supervisor. With these few words, I would like to request Sir to share his views on his topic. Today his topic is spectrally tunable dynamic light source, a component of smart lighting system. Sir, you can start your lecture. Please, sir.
Thank you, Dr. Abhik Mukherjee, and thank
Thank
you,
you, sir.
Oritra Ghosh, for introduction. I am honored to be invited here at this to deliver the lecture at this program organized by the Electrical Engineering Department, BP Poddar Institute of Management and Technology. This is my second occasion here in this college. It is always a pleasant opportunity to share experience with the colleagues, the same group of people, the faculty members. So I plan to complete my lecture within 50 minutes. Whether this entire screen is visible to all of you?
Yes, sir. Absolutely, it is visible, sir.
Okay, and it is moving.
Yes, sir.
Yes,
Sir. Fine, sir. It's already fine.
Thank you. So my plan to finish this lecture within 50 minutes, and then I'll be happy to for interaction. Um, so the topic is, as it is suggested, it is spectrally tunable dynamic light source. So the lecture coverage is I will discuss first what the basics of smart lighting system, the very basic, with some examples, and then I will discuss the scientific basis of what is meant by spectral tunable light source. What is the background theory, how it is achieved. My objective is to share the procedure, how to achieve this product actually that we have done at our laboratory. So I will concentrate more on the procedure and the methods. Then I will discuss on the color sensor, which is a very important component. With the I will finish with the spectrally tunable dynamic light source, its flow diagram and performance analysis. So before going into detail, let us talk about what is spectrally tunable light source. These two kinds of light source we are very familiar with. It is fluorescent lamp. The spectrum is like this, and it is tungsten filament lamp. The spectrum looks like this. It is not possible for us to tune the color of these particular light sources. What we can do, we can change the light output from the source, which is known as dimming. But this kind of light source we are familiar nowadays. It is very visible in the facade of any building system. These are called spectrally tunable light source because the basic component of this kind of light source is the RGB LED. Although the source looks like a single lamp, but there are three lamps. Red, green, and blue LED chips are here with a common cathode. So this is the diagram of this circuit diagram of this RGB LED, what we call the RGB LED. So these RGB LED, by controlling the power fed to these three channels, it is possible to generate a multiple color, wide range of colors, which is happening here. But this kind of RGB LEDs are mostly used for decorative purpose lighting. On the other hand, the other concept of lighting application is functional lighting application, which is used in the offices, in the residences, etc. For functional lighting application, this kind of light source is a LED light source where a combination of the two kinds of LED chips are there. This is the warm white LED source, and this is the cool white LED source. So by mixing, by changing the light output from the two kinds of LED chips, it is possible to have a wide range of color emitted from the lamp. This is actually the spectrally tunable light source. So basic physics behind it, a spectrally tunable light source must have more than one light sources within it, and we have to control the power delivered to the light sources to vary the component of emission from individual light sources. In that way, we can achieve the spectrally tunable light source. Now, the smart lighting system has the following components: the LED luminaires, sensors and actuators, and connectivity interface. Sensors and actuators are required to sense the, say, occupancy sensing, maybe daylight sensing, so that depending on the preset program, the light output from the LED luminaire can be varied, and everything is to be controlled with some wireless or wired interface. So interface, connectivity interface is there to lamps and sensors and actuators. But if we consider what the technical features of LED luminaires, there must be some options. What are the options? There must be some option to adjust the spectral composition, what we call the color tuning. There must be some option so that we can change the light intensity from the source, what we call the dimming. The concept of dimming is well known to all of control in the individual lamp or a group control is possible. And all these things, the connectivity either may be wired or wireless. So these features should be there for any light source that should be a light source compatible to smart lighting system. Now I will discuss two examples, one for residential smart lighting application, other for street lighting. Very brief. I have taken this from this reference, the typical block diagram. This is the lamp, and they have actually developed this app. And they call in any residence, the owner can select the light level according to the job. There are 9 activities they have mentioned here. Watching television, these are listed here. I'm not going to read out. So depending on the activity, the light level requirements are different. So they develop this app, and the app is based on this, works on this program, and basic component is this. So the microcontroller is the main control unit, and followed by a remote circuit. And actually, the microcontroller receives signal from the light sensor, which senses the ambient light, and the connectivity selection of the activity can be done either by a smartphone or any other input can be there with the help of the Bluetooth module. So the power source is here. So depending on the sensor received by the microcontroller sends the signal to the dimming circuit. That is what the power level at which the lamp is to be driven. So that lamp emits light output accordingly. So this is the block diagram of the smart lighting system as proposed by the researcher in this reference. So what is the flow diagram? So select after switching on the lamps, an activity is to be selected. So after selecting the activity, the ambient light level is to be measured by a light sensor. Then the sensor output is to be compared with the ambient light source, with the desired light intensity set by the microcontroller, and the adjustment of the dimming level is done by the control signal generated by the microcontroller to drive the light source. So here there is a checking box whether the desired light level achieved or not. If it is achieved, then N. If not, then adjustment of the level is going on. So this is the way their system actually works. Then I come to the next example of smart street lighting system. This kind of street lighting system already installed at NKDA, New Town, Rajarhat. Some portion of the street is there. This type of installation is there. The beauty of this type of road lighting installation is that a person, an owner, can operate the entire street lighting system at a far remote place through the connectivity in this way. So there are a number of features associated with this street lighting system. It is not only the dimming with respect to the time scheduling, it is dimming with respect to the traffic density. So to monitor the traffic density, camera is embedded in this system. So this kind of smart street lighting system can provide also a number of information about the instantaneous status of the load to the service provider to this connectivity network. There are a number of advantages of smart street lighting system. Apart from the time scheduling on and off, the intensity can be controlled, the remote observation is possible, and continuous monitoring by camera is possible. And in addition to that, the health of the street lighting system can be monitored from the far remote place. So this kind of smart lighting system has two-way connectivity. From the lighting system to the owner, or from the owner can control the lighting system according to this requirement. So with this brief introduction of smart lighting system, let us concentrate our today's topic on dynamic light sources. What is mean by dynamic light sources? With the help of dynamic light sources, an user can generate the color or intensity according to the requirement or desired preset values. It is capable to simulate the programmable light scene. So we can program it. We can think about a number of light scene, and accordingly the program is set into the microcontroller, and it can run following that programmable light scene. Time scheduling is possible, and of course the sensor must be there to sense the occupancy, to sense the daylight level, or to sense the light scene generated by the light source, what we call the closed tube lighting system. So we will concentrate our discussion on this daylight spectrum follower that we have worked in our laboratory. So before going into detail, I want to discuss some theoretical basis of what is called the spectrally tunable, because we want to change the color of light. So color must be presented by numerical values, otherwise we cannot program it accordingly. So numerical representation of color is a must. So I will discuss on it first, but before that, the very 2 or 3 slides I will share with you on the very basic of our color vision. We all know that our retina actually consists of 2 types of photoreceptors. One is rod photoreceptors, which is activated at very low light level, and at light level, the usable light level, the daylight level, the cones are activated. The cones are responsible for the color vision. But actually, we have 3 different types of cone photoreceptors. One group of cone photoreceptors has this peak sensitivity and the red region, or the red cone receptors. Other cone receptors shows the peak sensitivity in the green region. We call it green cone receptors. Similarly, the third one shows the peak sensitivity in the blue region. We call the blue sensitive cone photoreceptors. Actually, an observer with normal color vision can perceive 4 distinct hues: red, yellow, green, blue. And since we have a normal color vision is due to the 3 different types of cone photoreceptors, the human vision is known as trichromatic color vision. So the red sensitive, green sensitive, blue sensitive cone receptors are named as L cone, M cone, S cone. Here L is the long wavelength, long wavelength. You know that in the visible spectrum from 380 to 780 nanometer, the red lies in the higher wavelength region. That is known as long wavelength sensitive. So L cone. In the same manner, the M for medium wavelength sensitive, green, and S, that is small wavelength sensitive, blue. We should keep in mind this L, M, S cone. L means red sensitive, M green sensitive, S for blue sensitive. And the color vision model developed so far by the scientists, actually there are 2 systems, 2 channels are in the model. One called non-opponent achromatic system, and the second class is 2 opponent chromatic system. So let us look at the diagram. This is the color vision model. Whatever the color vision we have, it can be explained with this help of this model. There are 3 channels: the achromatic channel, achromatic means no color, and the 2 chromatic channels. I will discuss one by one, and it is S, M, L that I explained already. So let us first discuss on the achromatic channel. In the achromatic channel receives input from M cone and L cone, and the output depends on the retinal irradiance and wavelength composition. So these achromatic channels does not have any color information. It actually helps us to receive the brightness of any light source. On the other hand, the first blue-yellow channel, these 2 are known as opponent channel. Why opponent channel? Because here the blue-yellow opponent channel produces difference between the output of the S cone and the sum of the output of the L and M. You look, if you follow this diagram here, the response from the L and M cone are added, and these two are compared with the response of the received from the S cone. So this is blue and yellow. Why yellow? We know that when red is mixed with the green, it produces yellow. That's why it is known as blue-yellow opponent channel. Why opponent? Because the response is generated by after comparison between the signals from the two, the green, the yellow and the blue. Similarly, the third one, the red-green opponent channel, produces difference between the output of the N cones and the sum of the S cone and L cone. Since the percentage presence of the S cones are very less, it is known as red-green channel. So primarily it is the signal received from the red and the green. So these two opponent channels are responsible for the color vision, and these achromatic channels is responsible for the perception of the brightness that we have. The faculty members, who were actually working with the color image processing, you already come across with the color model. In the color model, you see there are three dimensional color model. The lab space LAP, CI lab space is there. There L for lightness, that is the corresponds to this achromatic channel, and A stands for plus minus A, and that is red green channel, and B plus minus B, that is blue yellow channel. So this is the basis of that. Anyway, another interesting point is that the output of the opponent class actually show either increase or a decrease in activity depending on the wavelength. See, this is the red-green channel. You see, depending on the wavelength, their activity either show increment or decrement. Similarly, for the yellow-blue channel, the activity either show increment or decrement depending on the wavelength. On the other hand, the black line, which actually corresponds to the achromatic channel, always show the increment depending on the wavelength. This is actually responsible for the basis of photometric measurement, what we call the V lambda. So with this background of the color vision model, we can conclude that there are actually three attributes of the color. What are the three attributes? The first one is the hue. The hue means the H, the color itself, the gradual variation from red to violet. The second one is the value, V, the gradual variation from white to black. And the third one is chroma, that is the gradual variation from pure color to white. So these three attributes, any color model must have three attributes to represent this hue, value, and chroma, whatever may be the name given to them. Now, how we numerically specify the color of a lamp? Actually, the chromaticity, it is very similar to the XY coordinate system, the first quadrant of the XY coordinate system. Here, the term chromaticity means the chromaticity coordinate. It is represented by two-dimensional values, small x and y. I repeat it, small x and y, because there are other x, y, z will come. There are capital X, Y, Z, meaning are totally different. It is the latest model as proposed by CIE, the International Commission on Illumination, but there are so many limitations of this model. So subsequently, the updated version is published in 1976. It is Q prime P prime. We for the timing we concentrate on this 1931 XY chromaticity model. Then another way of representing color of the lamp is correlated color temperature. This is correlated color temperature. This is the temperature expressed in Kelvin, the SI unit of temperature Kelvin. It is the temperature of the black body. It never represents temperature of the light source. It is the temperature of the black body at which the color of the radiation emitted by the black body is very close to the color of the radiation emitted by a lamp, right? Say for example, when we look at to the fluorescent lamp, we perceive white color. So if a black body and the technical spec of the fluorescent lamp, you may find one is mentioned at 6500K. That 6500K is the CC. So the meaning is that if a black body radiator is heated up to temperature 6500 Kelvin, then the black body emits similar color to the fluorescent lamp. And of course, this is based on the Wien's displacement law in the high secondary physics. The Wien's displacement law, lambda n is equal to constant. As we go on increase the temperature of the black body, then the peak radiation wavelength lambda n shifts towards smaller wavelength region, that is from red towards the blue region. Accordingly, with the temperature, the color of radiation of the black body actually changing. This is the basis on which the color of functional light, that is the tungsten filament lamp, the white LED, the fluorescent lamp, those are actually represented by the temperature of the black body and is known as the colors are correlated, it is named as correlated color temperature. But for saturated color, the concept of CCT is not applicable because from black body radiator, it is polychromatic radiation. So any monochromatic radiation cannot be represented by with the concept of this correlated color temperature. We will discuss on this and we will not discuss on this dominant present purity for the time being. Let us look at the 1931 XY chromaticity system. Actually, CI provided these two things. One is the chromaticity diagram. This is the XY chromaticity diagram. This is X. I think this is visible. This is small x and this is small y. The maximum value of small x is 1 and the maximum value of small y is 1, again 1. And the locus actually represents the XY chromaticity of the all spectrum color starting from 400 nanometer to 760 nanometer. So this is actually we call the spectral locus. And this is the locus of the Planckian radiator that we call the black body locus. So this locus actually shows how the temperature of the black body change from red to yellow, then yellow white, then bluish white as we go on increasing the temperature. So when the temperature CCT of the value of around 3000 Kelvin, the color is yellow white, very similar to the tungsten filament lamp. The CCT of tungsten filament lamp is 2800 Kelvin. On the other hand, the white fluorescent lamp, the CCT is 6500 Kelvin. That is called cool white and warm white. And these data actually corresponds to the sensitivity spectral response of the red photoreceptors, cone receptors, green cone receptors, and blue cone receptors given by the CIE, and this is given in mathematical form, in tabular form, so that the computation can be done with the help of the program or other mathematical help. So this is the pictorial representation how the chromaticity is calculated or measured with the help of a colorimeter. So in the colorimeter, there are 3 different types of light sensors: X lambda, Y lambda, Z lambda, which are actually simulating the spectral response curve that I discussed right now. And the radiation from a test lamp allowed to incident over the 3 different color sensors, and ultimately what we get the capital XYZ. Mind it, it is capital XYZ. This actually represents how much amount of red radiation present in this radiation. What is the green amount present in the radiation? What is the blue amount present in the radiation? So after getting the values of XYZ, small x actually is capital X by X plus Y plus Z. So it means small x is the fractional composition of the red present in the radiation. Small y is the fractional composition of green present in the radiation. This actual XY is actually the chromaticity. So our objective is how to find out the chromaticity, and from chromaticity how to find out the CCT that we need for the development of the dynamic light source. The second way of the getting chromaticity is with the help of spectrophotometer. Again, the purpose is to get the capital X, Y, Z, the tri-stimulus values, and then the chromaticity. This is the mathematics, what I explained right now. The slides will be shared with you, all the participants, so you can see the slide later in detail. So this is the example with the tungsten filament lamp. The data of spectral power distribution is available in this form, and we can measure these tri-stimulus values, and finally we get the chromaticity values like this. And after getting the chromaticity value, what is the use of this diagram? After getting the chromaticity value, if we put, if the point is here, then the color associated with that point gives the color appearance of the lamp. So this is the usefulness of this chromaticity diagram. And there is a mathematical formulation to get the chromaticity U prime V prime from the chromaticity XY. This is the formulation. Now, after getting the chromaticity XY, it is possible to calculate the CCT value with the help of this polynomial. This polynomial is proposed by the McCammon 1992, which is known as McCammon formula for CCT computation, where input is the chromaticity of the test light source and the output is the CCT. Here T is the CCT. However, the model actually works within this range, 2000 Kelvin to 10,000 Kelvin. Now, let us have a. Now we go to the how we get the color tunable light source. Actually, the color tunable light source can be obtained by various means with the help of RGB LED lamp, or RGBW means white LED lamp, and RGB amber for amber LED lamp. But this kind of lamps are used for decorative lighting application. For functional lighting application, the color tunable light source can be achieved with the help of warm white, the combination of warm white LED and cool white LED. Whatever may be the light sources we use to get the color tunable light source, the basic mathematics of color mixing is provided by the formulation of Grassmann. We call the Grassmann's law of additive color mixing. This formula is given by Dr. Grassmann, and we actually in practice we are not using this formula. We are actually using this formula because here we can add the contribution from n number of light sources. You see the formula here. K xk yk is the chromaticity of the k light source, and yk is the one of the y stimulus value of the k light source. So with the help of the chromaticity and y stimulus value of the k light source, it is possible to get what is the chromaticity of the mixed radiation. These two are the chromaticity of the mixed radiation, where n number of light sources are mixed, right? So the color mixing law, from this color mixing law, we actually get the chromaticity of the mixed radiation. So this law is very useful to develop the dynamic light sources. So the dynamic light source that we have we worked with at our Jadavpur University lab actually composed of a group of warm white light LED, warm white LED stream, and the cool white LED stream. This is the spectrum of cool white LED stream. Blue component is relatively higher. Here the warm white LED array, the red component is relatively higher. So the color tunable is achieved by mixing of the radiation of two different kinds of spectrum. This is the you see two different kinds of spectrum. By mixing the radiation coming out from the two lamps, we actually achieved the color tunable light source, what we call the dynamic light source here in this presentation. These are the measured parameters. CCT, we measured it. So see, the CCT of the warm white is 2840 Kelvin, and that of cool white is 5750 Kelvin. So it is possible to get the wide range of CCT variation with this lower limit and upper. In our case, actually we varied from 2900 Kelvin to 5600 Kelvin in our case. So it is possible by mixing. This is the lower limit. So lower limit and upper limit of the range is decided by the CCT of the individual light sources. Um, the DLS is the dynamic light source. Let us discuss how the dynamic light source actually works. At the beginning, we have to set the desired illuminance and CCT point. That means what color we actually want to get from the light source and how much light we want to get out of that source. So with this information, it computes chromaticity coordinate by taking the CCT of the individual sources. So it is the input. So computation of chromaticity coordinate is done with this value, and the blending ratio is to be computed with the help of Grassmann's color mixing law. And again, the illuminance contribution again is to be computed using the Grassmann color mixing law. And accordingly, the duty cycle is to be computed. To obtain the duty cycle, the desired duty cycle for a specific light output, we need to get it from a data which already fed into the system. Cup fitting. This cup fitting actually, what is the data? It actually gives us it is the duty cycle versus lumen output. This cup fitting actually duty cycle versus lumen output for the warm white LED chips and the cool white LED chips. So depending on the desired duty cycle, we need desired light output. We need to find out what is the duty cycle required to drive the individual LED arrays. So individual LED arrays are driven with the computed duty cycle, and ultimately we get the system out. Flow diagram. The dynamic light source is tested with 4 discrete set of CCT 2900 to 5600 and 4 discrete set of illuminance values. So total 16 discrete points are tested with the help of this dynamic light source, and you see the square actually is the set value and rhombus are the measured value. Here they are very close, but some deviations are observed in these points. See, this system is actually the open loop system, and we will see this difference will be minimized when we upgrade this particular system with the help of a color sensor operating in closed loop connectivity. Now, apart from the discrete 16 set points, we again tested the light source for continuous time variation. So, x-axis here the time scale from 0 to 60 minutes. For the both cases, here it is the variation of the CCT, and here the variation of the light source. Actually, these two are the same, are occurring at the same instant. Actually, the open symbol is represents the desired value, and the closed represents the measured value. They are very close, but some deviations are observed in case of here. So this is the flat desired, right? Here the illuminance, our requirement is a flat from 48 to 60 is flat, but here we see the fluctuations of the illuminance value. We see in our system, we see that the cool white LED systems are not reliably are not giving out reliable output when the dimming level is very less, and the deviations are due to for that reason. So the limitations of the open loop systems are, we notice the following limitations. It is incapable of monitoring the instantaneous achieved CCT and illuminance. It is incapable of addressing the effect of temperature variation of spectral composition and lumen output of LED. And I think you know that all the performance of LED, declared performance of LED, are laboratory tested at 25 degrees centigrade ambient temperature. But in practice, when the ambient temperature differs from 25 degrees centigrade, the spectral composition of light and light output of all the LEDs are differed. So the any open loop control system with the help of this open loop control system, it is not possible to address this variation of spectral composition and light output due to the temperature variation. Again, it is incapable of adjusting the lumen depreciation and spectral variation due to aging, what we call the lumen depreciation. So, to upgrade our system to the closed loop lighting, dynamic lighting system, we need to take help of a color sensor. We actually work with this color sensor, ECS3475, for closed loop operation. I will now explain how we actually calibrate the color sensor, and ultimately we apply this color sensor in our system. This color sensor actually the 4 channels: red, green, blue, and clear. These are the spectral response, relative spectral response of the color sensors, and it communicates through I2C protocol. Now the question is how can we get the chromaticity value and CCT value? Here we need to recall what we discussed just before, how we get the chromaticity coordinate and CCT value. Now from the RGB color sensor, actually we get the RGB values. And with the help of RGB values, by correlation matrix C, we convert it into corresponding XYZ values. So this is the mathematics. So with the help of RGB values and the correlation matrix, we can get the corresponding XYZ values. These XYZ values, when these XYZ values are known to me, I automatically calculate the chromaticity XY value. So once chromaticity is known, using that kind of formula, I get the CCT value. So in this way, from this color sensor, ECS34725, we can get the instantaneous, the information of the color and the illuminance value. How we get the illuminance value? I will tell you. Again, I repeat this. The illuminance value is to be obtained from this right hand. Now, how we calibrate it? Actually, for the calibration purpose, we need to get the numerical value of the correlation matrix. This numerical value of correlation matrix is obtained by laboratory testing conducted at our lab. Here, RGB are the sensor output, XYZ are the measured tri-stimulus value. So this is the measure for the lower, intermediate, and higher CCT points. Actually, 3 distinct CCT points we need to consider. One is lower, another is intermediate, another is higher. So these 2 lower value and higher values is selected based on the considered or taken the individual, the warm white LED chips and cool white LED chips. So as I mentioned in our earlier slide, the measured values of CCT of the warm white and cool white group decide the lower value of CCT and upper value of CCT. And this intermediate value of CCT is taken. So the dynamic light source is set at 2900 Kelvin. At that position, we need to get this RGB value from the sensor and this XYZ value from an instrument what we call the CL200 chromometer. So this instrument we need to get the value of the C, correlation matrix C. Similarly, when we set the dynamic light source at 4200 Kelvin, we get the RGB value from the sensor and correspond XYZ value from the chromometer used in this system. Similarly, for higher range. So these are the numerical values. So this matrix is given by the color sensor, and this matrix is obtained with the help of CL200 chromometer. And ultimately we get the correlation matrix. So once this correlation matrix we get, so during measurement, instantaneous values of RGB RGB obtained from the color sensor can be converted to XYZ value with the help of program embedded in the microcontroller. And the illuminance values is obtained from this formula, right? So this is the procedure by which we can calibrate the color sensor before using it to our system. Let us come towards the closed loop dynamic daylight responsive dynamic light source. This block actually the daylight responsive light source. This is the dynamic light source. We call it daylight responsive because the program is set so that it can follow the instantaneous color property of the daylight and the light level of the daylight also. So we need actually two sensors. The first sensor is the external sensor SEXT. I think it is visible to you. SEXT. This is daylight sensor. This daylight sensor actually measures the external daylight. And here the internal light sensor SINT, it actually measures the radiation coming out from the dynamic light source. So with the help of external sensor, the daylight color temperature of the daylight and light level of the daylight is obtained by the color sensor and fed to the control unit. And accordingly, the control unit accordingly the DC duty cycle, DCW duty cycle for warm white group and DCC duty cycle for the cool white group. And accordingly, the duty cycle for the warm white group and duty cycle for the cool white group is calculated in this control unit, and it drives the warm white LED array and cool white LED array separately. So depending on the duty cycle, the emission from the warm white LED group and cool white LED group are controlled, and we actually get the light output from the dynamic light source. This light output again monitored by the internal light source. So this is a closed loop path. So operational flow diagram. Let me explain this. At the beginning of the initialization of system, the dynamic light source is set particular value of CCT above 5000 Kelvin at particular values of illuminance. What is called, we call the initialization of the system. Then a light source measured the instantaneous value of CCT luminance. Those are the function of P because it is instantaneous. It is variable. The addition of P. Then compare the measured data with the preset value, and accordingly the duty cycle is to be adjusted, computed to get the desired point. So then the measured values are done. Measured values of CCT and illuminance is obtained by the internal sensor and then compared. If the deviation lies in the tolerance within the tolerance value, then we call the yes, we achieved the desired set point and we see the output of the system. If not, the iterative path is there, it follows the iterative path, but with a maximum number of loop because it is a continuous system, daylight is ever changing. So we need to break the iterative loop when n equal to n max. The value of n is set about 20 to 25. Right? So this is the operational flow diagram of the closed loop daylight responsive dynamic light source. Here the CCT and the light level actually followed by the dynamic light source. What is our requirement? We set the program like this. The dynamic light source follow the CCT of the daylight, but the lux level actually follows the reverse pattern. So when the external light level shows increment, our system light level should show the decrement, just reverse pattern. So we will see with the results. So this is the experimental setup. Here you see the external light sensor at the outside of the window. This is the magnified image of this sensor. This is the external light sensor, and this is the daylight responsive light source, and the internal cell is mounted here to monitor the radiation coming out from this light source, and it is kept within a dark box so that no light actually pass from what it is a gave photograph of this setup, right? But actual during measurement it is closed and dark inside, so that the internal light sensor only the light from this light source. We perform two different types of what we call the laboratory testing. So this is the laboratory testing. This is the time variation pattern. The circle, field circle is the required value. The rhombus is the measured value. The first diagram corresponds to CCT. So see, the CCT actually follows from this set point to this set point. The variation follows this path, right? Similarly, from this set point to another set point, this is the path of the CCT to converge from this point to this point, actually. So the upper diagram actually shows the CCT path, and the lower diagram is the corresponds to the illuminance path. How it follows from one set point to another set. And you see the difference between the open loop system to closed loop system. In this closed loop system, the required value and measured value are very close to each other. And this is the in situ testing. This testing was conducted during daytime at 3 different times. This is from morning 9 to 10. One for CCT and second one for lux. This pair is for 11:30 to 12:30, considering the 12 noon, and this pair corresponds to 2:10 p.m. to 3:10 p.m. 3:15 p.m. like this. Again for 1 hour for the CCT and lux. So let me explain. So these actually, these are the legend. The circle actually external light sink. The square actually required value, and rhombus is the measured value. So far as CCT is concerned, CCT measured value of CCT are very close to the external CCT values throughout the time. Very close, actually overlapping. That's why nothing is visible. But in case of lux, it shows the incremental pattern with time. So it is increases with time. So our dynamic light source shows decrement over time, right? Just reverse pattern. While during this 11:30 to 12:30, the lux level of the external light source shows the more or less same constant. Here also it is more or less same constant value. Here the external light level shows the decrement here, and our system actually, the light output actually shows increment. So with this result, it is established that with the help of the color sensor, it is possible to follow the external, the CCT of the time varying CCT of the daylight and the time varying light of the daylight of this dynamic light source. Again, this plot actually we have to present the deviation with the help of this diagram. Whether the deviation lies within these two boundary. This is the upper boundary and the lower boundary. This actually that the deviation, whatever may be the deviation in our system, that actually is the accelerated. So what we discuss is that the daylight responsive dynamic light source is capable to follow the instantaneous color temperature of the daylight and the light level, but this is the beginning of the work. So more feature we can add here. So there is no interface with the with the mobile smartphone. There is no app yet to be developed for this system. So there are so many things, so many features we can add with this system. But basic thing is that basic product of light source that we have already developed and tested. Yes, it is now it is ready to fit into the system and to make it enable to the smart lighting system. So our work already published here. Those who are interested to have the details of the system, you can consult. So in this lecture, what we discussed briefly is that what are the features of the smart lighting system and what is meant by spectrally tunable dynamic light source. What is the advantage of spectrally tunable dynamic light source, and how a system can be obtained in practice in laboratory. So my dear faculty members, you are always welcome to come forward, because the domain of this like science and engineering is open to the computer professionals, for the development of apps, for the communication professionals, the electronics and communication engineers professionals, because so many communication, so many connectivity interfaces there. It is not only the domain of electrical engineers and optical engineers working in this field, and it is open. So you may think about it. And what we now in this work, in this brief presentation, I have tried to present a system, about a system that we have developed in our laboratory. So to this is the reference I have consulted to compose the presentation. So before conclude, I must thank to again to Electrical Engineering Department of the BP Poddar Institute of Management and Technology, especially to the head of the department, Dr. Namita Sannal, and
thank you, sir.
Dr. Abhik Mukherjee, my student, and as and also
thank
all
you.
the participants.
Thank you very much, sir. Thank you very much.
Thank you very much, sir, for your wonderful speech. Now we will have a short question answer session.
Yes.
If you have any doubts, any question, you can ask. Just you have to unmute yourself, and then you have to place question. You just have to unmute yourself, and you have to place a question.
Auditra, I'm having one question.
Yes.
Sir, I just wanted to know that the module that you have developed, DLS module, what is the efficacy of the DLS module?
Oh. Efficacy, that movement forward, right?
Yes, sir. Yes, sir.
This is the lumen. This is the warm white LED. This is the lumen we measured 648 lumen. And power is counted to power 8. So by dividing it 648 by 8, we get the efficacy for warm white LED and now this
But this is for the entire DLS module.
Actually, DLS module consists of two groups. One is warm white LED and other is cool white LED. And this data is for entire group.
Okay. One more thing. How luminous efficacy is optimized for a particular color CCD?
Actually, luminous efficacy cannot be optimized in our application. It is luminous efficacy is the manufacturer's data. It cannot be. We cannot optimize it. We cannot change it.
Okay.
Stable information.
Sir, one more thing. There are many health issues when we are using these LEDs. So, considered all the parameters while developing this?
Yes. Because see, if you see this white LED is obtained from the phosphor-coated blue LED. It is not for UV. There are so many ways. One is from UV with phosphor we can get the white, but here from the blue we get the white, and the power is less. And again the diffuser is there, and it is to be mounted at a very longer height. So it is no way it can damage our system. No way.
Okay, sir. Thank you, sir.
So again, I will request anyone who has questions. I'll request anyone.
So I request Dr. Nobita Sannal to share my presentation with the participant faculty member, and my email is there. If they have any questions, they can email me.
Okay, sir.
Yes, definitely, sir. I will circulate that PowerPoint presentation to every participant of this FDP, and I would like to also share with you a fact that some person from Dostur are also present in your presentation. They specially asked whether they can be present in your presentation. So we have said yes, definitely, because every time we need an industry academia collaboration. So your talk is very illuminating, and thank you very much.
Again, I will request anyone have any question, you can ask. So, okay, sir. Now I will, without a further ado, I will request Ms. Chandani Das, Assistant Professor, Department of Electrical Engineering, to felicitate our honorable speaker.
Hello, am I audible?
Yes, ma'am. Absolutely.
Okay, thank you, Orithro. Good afternoon, everyone. Thank you very much, sir, for giving your valuable time and for such a beautiful lecture. It was enlightening, engrossing, and I'm sure we all have thoroughly enjoyed it. It helped to kindle our renewed enthusiasm in optics. Now I would like to request Ms. Shushmita Dey, Assistant Professor of our department, to come forward with the small token of appreciation, a certificate for you on our behalf. Shushmita, please share it on screen. Thank you, Shushmita.
Nice.
Thank you, sir.
Nice. Very good.
It was really a pleasure to have you with us, sir.
Thank you.
Sir, it will be sent to you by email.
Thank you.
Okay,
Welcome.
sir.
Bye.
Bye, sir. Now I request Orithro to continue with the next session.
So I think we should request all our participants to put their video on so that we can have one photograph session if sir is there.
Sir has left, I think so. Okay, just honest to wait. I'm just calling sir. Okay. Yes. And when sir comes, please give him a big round of applause.
Yes, sir.
Okay, wait, sir is coming. Oh, he has joined. Okay, thank you, sir.
Yes.
Sir, please turn on your video. We will have a
Video is
photograph session.
on.
Yes. Yes.
Big round applause for
Thank
sir.
Okay.
Thank you so much, sir. Thank you.
Thank you, sir.
Bye. Bye.
Bye,
Yes.
sir.
Okay, please, all the participants, please again turn off your videos and your microphones. We are about to start our next session. It's a great privilege and honor to have with us Dr. Abhik Mukherjee, Associate Professor in the Department of Computer Science and Technology, IIEST, Shibpur. I would request Dr. Sudipta Chakraborty, Associate Professor in the Department of Electrical Engineering, BP Poddar Institute of Management and Technology, to introduce our honorable speaker.
Thank you, Anushri. Am I audible to everyone?
Yes, yes, you are.
Yes, ma'am.
Very good evening to all our dignitaries, our participants, the audience. Well, I'll speak a few words about our speaker. Dr. Abhik Mukherjee is affiliated to the Computer Science and Technology Department of IIEST Shibpur since the last 20 years. He is an alumnus of the Department of Electronics and Telecommunications Engineering, Jadavpur University. He has few years of experience in the IT industry and research experience in Indian Statistical Institute, Kolkata. Dr. Mukherjee has successfully executed some control systems projects of DRDO. He regularly teaches subjects like analysis and design of algorithms, information and coding theory, simulation and modeling, and various other subjects for the UG and PG students. His research interests include estimation of dynamical systems and various aspects of information theory. The topic of his talk today is Emergence of Coding Theory-Based Cryptography. Now, cryptography, as we all know, is the practice and study of techniques for secure communication in the presence of third parties. Originally, it was the science of hiding information, but now it has expanded far beyond the goal of keeping the data confidential. Now it includes checking integrity and authenticating both the data and the sender. The commonest example of application of cryptography in day-to-day life is in the electronic money that we use. Now, coming to electrical engineering and allied fields, cryptography has extensive usage in the smart grid. The smart grid enhances the functionality of the power delivery system using sensors, communication, computation, and control. Intelligence is imparted to the grid in the form of control through feedback, or in other words, by using two-way communication. Now, internet is being used for communication purpose. However, using the internet means vulnerability to cyber attacks, and protecting the grid is a challenging task. Because once the system is attacked, the attacker may control several meters or disrupt the load balance of the system. Thus, we need to gain complete knowledge about cyber security so that the security hazards can be eliminated. Now, over to you, sir, Dr. Mukherjee. Hello? Hello?
Hello,
Did I get disconnected?
No, you are there. You are there.
I'm there, na?
Yeah.
Dr. Mukherjee isn't there?
I'm just checking.
Give me one. I'm just clarifying. You
Okay.
checked?
Yes, yes.
Abhik Mukherjee is not there.
But yes, it is showing in the participants. I don't know whether it is sir or not. Abhik M. someone.
Okay, yes.
Abhik Mukherjee, right?
Yes.
Yes.
So he's
yes.
Yes, he has
he has
Yes.
joined. He has joined.
Yes, I have joined.
Yes, sir.
Yes, sir.
আর কিছুই আসছে না
Yes, sound is okay.
Sir, please unmute yourself and you have to share the screen.
Yes.
At the bottom right hand corner there is present now. You have to press that.
যায় ও এটা গেলে আমার এটা সিলেক্ট
Yes, sir.
Yes, sir. It is visible, sir.
It's visible now. Yes,
Okay.
sir. Visible. Yes, sir.
Okay. Audible also?
Yes, sir.
So I can start?
Yes, sir.
Yes, sir.
So good afternoon everybody.
Good afternoon, sir.
Good afternoon, sir. This is lecture which is coding theory based cryptography. Now the contents are as follows. We would be discussing briefly about the public key crypto system and linear block codes so that we can bring the relation between the two, and therefore after brief introduction to the crypto system and the linear block codes, we would be introducing the code based cryptographic scheme which will be based on GOPA codes, a special kind of linear block code which is resilient, found to be resilient for the application of coding theory based cryptography. Then we would get into the crypto system which was developed by McAleese on the GOPA codes. Different attacks on that crypto system we would discuss, followed by the derivator crypto system, that is the signature equivalent of the McAleese crypto system. And finally, we would see why this is emerging as a topic in the post-quantum era security. Okay. So, I have assumed a zero background for the audience. Maybe many of you have full knowledge of these systems, a public key crypto system, but I put a brief introduction so that everyone can appreciate the later part of this lecture. So the basic idea here is that there is a concept of a public key and the private key. If you look at this picture, then it will be clear. So the sender is trying to send some plain text to the recipient. In between, there is one encryption process where the recipient's public key is used, is applied on the plain text to generate the cipher text, and that passes over the channel. At the other end, the recipient has to use own private key to decrypt this message back to the plain text. So the message is encrypted using the public key of the receiver, which is common knowledge. Every public key is common knowledge for both the sender, receiver, as well as any eavesdropper. They will know about what is the public key. That is the challenge, basically. So the ciphertext is generated, it is passed over the channel. At the decryption level, what is done is S of P of M, you retrieve the M. So S is basically kind of an inverse function over what P does. So S and P, so S inverts the action of P so that the ciphertext is giving you back the original text. Now, the signature encryption and decryption is another part of this. So, in the signature encryption decryption, what we do is we encrypt the signature. So, here the question is whether the sender is authentic or not. In order to prove the authenticity, the sender has to encrypt own signature using the private key. And then the signature can be decrypted by the recipient with the public key of sender. So supposedly the recipient is with her private key, and then this passes over the channel. Bob uses Alice's public key to verify the signature. So if it is not sent by Alice, then what would happen is that this signature verification will fail. So now one of the earliest crypto systems, and which is still popular with us, is the number theory based crypto system, public key crypto system. RSA stands for the three mathematicians who developed this system. So here you choose two distinct prime numbers. How large are they? They are basically today 128 byte, 256 byte numbers. Prime number is dense in that region also. There is a proof for that. And so then you compute n as a product of these two primes. And phi n is p minus 1 into q minus 1. E and D happen to be multiplicative inverse of one another in that phi n. So E is the multiplicative inverse of E modulo phi n. So with this much of mathematics now, what happens to be the public key is the N and E. So N and E is public knowledge, and the private key is N and D. And the whole idea here thrives on, now if you see C is M to the E modulo N and M is again C to the D. So if you are performing C to the D, then basically it is M to the E into D. And as I said, E and D are modulo multiplicative inverse. So E into D would result in a 1 so that you can retrieve the message. So that is the way they are able to retrieve the message using a E at one end and D at the other. Now, how can you attack basically this type of a system? So if you want to attack this type of a system, or it is actually secure because in spite of your knowledge of N, unless you are able to factorize N into the P and Q, that is the two prime factors of N, you cannot get to the phi N. And if you cannot get to the phi N, in spite of knowing the E, you cannot know D. So the attacker would be able to factor N into P and Q, then phi N can be computed, and then from E, D can be computed. Now for a classical computer, this factorization of large integers, as I said 128 byte or 256 byte integers, there is no polynomial time method for factoring such large integers. Now in 1994, that is 25 years have passed since Peter Shor has shown, that is a very difficult to understand proof is there, through which he showed that the quantum computer would be able to factor in polynomial time, and it will be thereby breaking the RSA crypto system. Now this is not even a big deal on standing on today. The quantum computer that has so far been implemented by IBM it is able to factorize 15 into 3 and 5. So that is the level of little kind of computation they are able to do today. But the risk is always there. So if the and just whenever the quantum computer is developed, the whole system is going to break. So that's why people are looking for solutions beyond the RSA. Before we go further, here is the typical information flow. You can see Alice and Bob, the public key is shareable and the private key is locked with Alice and Bob separately, and they this is the way, and they are sharing the public key through which the data they are sharing, and from there also sharing the ciphertext. This sometimes helps us to understand the information flow. Now coming to our issue, that is in the post-quantum era, cryptographic system has to be some system which will be hard to break using the quantum computer. Now Macauley's cryptographic system happens to be one very interesting candidate for the post-quantum cryptography. So we are going to see how the Macauley's cryptographic system can be implemented, what are the merits, demerits over the next few lectures. Before that, the linear block codes. So linear block codes is so you have a k-bit message which you add n minus k bits of redundancy to get to a n-bit code word. Now this very definition that this is a k-dimensional subspace of the n-dimensional vector space, this means that the code words have a closure property amongst themselves. So because of this closure property, so any addition of two code words, addition here we would be only considering binary codes, so that addition means the XOR operation. So addition of two code words would result in a word which also happens to be a member of this k-dimensional subspace. So that is also the reason we call this code as linear. So this class is considered to be linear operation, and then there is a closure property that is there. And if you look at the properties of this linear block code, then one very important property from where the parameter is also coming, the design parameter is also coming, is the minimum distance of the code. So the smallest distance amongst two valid code words. So that is important. Why? Because if you do not keep that distance, then any noise that comes through the channel, so you get a received word which is not a valid code word. So the whole idea of decoding is that the received word should be mapped to a valid code word. So the basic idea of a decoder naturally would be to just look at the distance of the received word from all the valid code words, and whichever code word is closest, you just decode it into that particular code word. You fall for the code word which is closest to the received word. That is the whole idea about the coding, the linear block codes, how they work basically. So the Hamming distance in case of the binary codes, which also can be, it can be shown that the minimum distance is equivalent to the minimum weight, Hamming weight. So that is the main property on which the linear block codes are designed. So what kind of distance you want to have among the valid code words, that is the design parameter. And the whole design, when you perform, there is a generator matrix which is used for the encoding part, and the parity check matrix. Then received word by the transpose of this parity you get the syndrome, and from the syndrome you can just do the okay. And systematic means where the message so nowadays like this. What is the decryption? The decryption is can be done by someone who has the knowledge of P and S. So with the knowledge of P and S, what they would do, the first step would be to get into Y P inverse, so the inverse of P. So whatever this P did is now gone. So now basically the error locations are scrambled, they are permuted to some other place. Now you know about some kind of a error correcting algorithm. Using that error correcting algorithm, this Y prime, you can get to the E prime. You can generate the M prime and you can get to the E prime, which is not exactly the E, but a different permutation of that. So in order to get to the original message, now you have to apply the inverse of S. So once you apply the inverse of S, S to the -1, the -1 somehow is not really prime. Anyway, so the to get the original message, you have to perform that and you will get back the original message. So it looks that simple. Now what are the attacks basically you can perform? So if you can guess the S and P matrices, that is all possible permutations of the S and P matrices, that will yield the code. So the attacker would be basically sitting with a high power computer and try out all the possibilities of S and P. This is a binary matrix. So all possible permutations, that is one way to attack the system. Another way is that the eavesdropper could be doing an exhaustive code word comparison. As I said, these are based on the distance matrix. So basically they would try to find out the closest match from where they can try to guess what was transmitted. Then the syndrome decoding, they can also perform the similar approach, and then sometimes what they do is they try by starting k correct and independent random positions, then perform bit swapping to get to the possible message. Multiple encryption is a big trouble in this type of system, because suppose the same message you are encrypting several times. the philosophy was to introduce random error. So at one point of time you introduce some E, and at another point of time you introduce some E dash. So then if the eavesdropper is getting these two encrypted messages, and if they somehow know that this is multiple encryption of the same message, then by looking at the positions where it is 1 and where they agree, Y and Y dash agree, and where Y and Y dash disagree, from there they can guess the message, the same one which was transmitted over and over again. So you give me more encryptions of the same message, I would be able to track what message you are trying to send. So it is suppose an attack or retreat in some kind of a fight going on. So then there is a computing sent over and over again, that is a vulnerability. Now this system has been studied since 19. System began implementations include registers and modulo 2, that is XOR gates and gates. It is easy to integrate also this type of system. But multiple encryption, as I showed, is a big weakness which we have to actually rectify. And then one interesting thing is that here the ciphertext messages are longer than the plain text. Why? Because this is actually the redundant bits that have come inside. Size of the key is very large because the size of the key are those large matrices, E and S and G. These are matrices, so they have functionalities, and so this size is enormous. In RSA, the size is not that, because E and D, so that 128 byte primes and their multiplicative inverse. So that way the size is, there is a bound on the size. Here, if you increase the size of the matrices, so the size will also grow, the quadratic. And initially, for many years, there was no obvious way to use signatures. And so unless you also can give the signature system, then the publicly crypto system looks incomplete. So now, if this type of coding theory based cryptography has to survive, so you cannot just about use an arbitrary linear code. The code that you have to use should be having some kind of special properties, so that the to the closest complex problem, basic computers as well as the quad. And the decoding of the code word should also look like a code been analyzed, remain deadful. So I just glance through how the binary OPA codes can be designed. Basically, I would be using a small example instead of going through the difficult polynomial expressions for now. It's difficult without the board also. So you have to use a Goppa polynomial, which happens to be basically the generator polynomial to be used for this code. From this generator polynomial, you have to get to the generator matrix, and then your code is ready. Now this has to be designed in any q to the m Galois field, and we would be using 2 to the power 4 for our exam. And so n, k and d would be the parameters. As usual, n is the code word size, k is the message size, and d is the distance. So based on that, based on the properties of this particular gz, that is the generator polynomial, you can find out what is the distance, minimum distance for this code. Now some special cases can also be designed for this particular codes, through which you can tune the the generator polynomial can be tuned for some kind of giving more resilience to the intended application of cryptography. And from the generator matrix you can also get to the parity check matrix. Here is one example. That the example is comfortable rather than those mathematics I think for now. So the GZ, that is the Gopa polynomial, here we are using in this z plus alpha to the z plus 1. This alpha is a primitive element of the GF to the 4. So from there we have factorized the z squared plus alpha to the 7 z plus 1. You will see there are two roots, z plus alpha and two factors, z plus alpha and z plus alpha to the 14. So alpha and alpha to the 14 become the factors of this. So from there, if you do some analysis, then you will see that here the message size is 4, n is 12, and t, that is the error correcting capability, that is 2. And so the minimum distance which happens to be now 2t plus 1, so that is greater than equal to 5. So this becomes our Gopa code. And if you now try to generate the parity check matrix for this code, at the very bottom you will find that there are two rows of this parity check matrix and there are 12 columns. So each row, as I said, this is GF2 to the 4. So the corresponding elements, if you write the alpha to the 9, alpha to the 10, etc., if you write down in the column form, so it becomes 8 cross 12. So it is the H matrix written in the GF2 to the 4 format using alphas. It is 2 columns. Now these 2 columns, 2 rows, they expand to now 8 rows. So there are 8 rows and 12 columns. So this becomes the H matrix. Obviously, this is a toy example. If you have to use it for cryptography, you can immediately see that if this is the H matrix. So it is 8 cross 12. So you can count out in substitution to get to H in order to guess the code. So from H you can get a matrix. So it looks like this, and it is that simple now. So you have the parity check matrix. This generator matrix, as you can see, there are 4 rows. So basically 4-bit messages, all possible combinations of these 4-bit messages can be generated using this particular generator matrix. Now suppose you want to send a message 1111. So what will be the code? Now here, if you look at these rows, if you add them in the modulo 2 addition format, so the leftmost is 1 plus 0 plus 0 plus 0, so it is 1. Next one is there are 3 ones, so it is also 1. Next column there are 2 ones, so it is 0, like that. The last one, etc. So then you can add some errors and you can try out some received vector. So from there, this type of exercise you can perform on this particular code. Now for the decoding part also, as we said that the standard decoder of the Gopa code, or for that matter any such linear block code, can be used, and using some particular decoding algorithm you can get back the transmitted information. Now we can get into the Macaulay crypto system, which was based on these Gopa codes. So for Macaulay's crypto system, now we can write that G is the generator matrix of the binary Gopal code. So now you will multiply M with this generator matrix to create a code word at some arbitrary error vector. So that provides you with a ciphertext MG plus E. Then this G basically, if you want to hide this G, so you have to pre-multiply S matrix and the P matrix, and then it will randomly shuffle and permute matrix, and then you will use this particular G prime. And then for the decryption part, as I have said already earlier, from the P parts,
Sir, are you there? Abhik sir, are you there? I think sir has lost connectivity.
Yes, I think so.
But
Okay,
sir is there.
Yeah, he's there. I'll just call him. He might have because of the weather. The weather isn't good at all. So might have lost connectivity. So I'll just ask sir.
Okay.
So I'll request everyone to please have some patience because the weather condition is not so good, as you all know. That's why this interruption will occur.
Oritra and Anushri, could you please tell me what was the last slide number? From where we can't, we have not been able to receive the audio.
Oritra, have you followed? I have
Yes,
not
obviously.
followed.
Error correction. Shudipta, error correction. Error correction. It was error correction.
Before error correction and decoding is there.
We can wait for some more time, 5 minutes, 10 minutes.
Please have some patience. He's trying from
Yes,
this end.
because it is tremendously raining.
Because the weather is not at all good. It's raining tremendously and he's trying his best. Please.
Sir joined already. Sir joined already.
Okay.
Shona Chevar?
Yes, sir. Yes, sir. Yes.
So possibly again I have to share, no?
Yes, sir.
Yes.
Present now your entire screen. Then you get to the screen. Now it's okay? Is it okay?
No. Till now, not okay.
Now it's not coming, sir.
Lights are not visible.
Just
Light not visible?
No, sir.
Lights are not visible.
Share. Now?
Present now.
Now?
Yes, it is coming. Yes, sir.
Visible now. It is visible now. Yes, sir.
So where?
Decoding example, sir. Next slide. Next slide, sir.
This one?
Encryption. Sir, the next slide, sir.
Public information, private
No. I think, sir, encryption from. Yes, sir. Yes.
Okay. So, hello. Now for a binary Goppa code, you have to take this generator matrix. Then you have to hide the G. So you will be using one S matrix and a P matrix, and use the G prime, which is S into G into P, to get to the ciphertext. And then for the decryption part, what you have to do, you have to use first of all the P inverse, and then you use the delta, which is some algorithm, some decoding algorithm, and then you will be applying the S inverse, and finally you get back to the N. So public information is the K cross N matrix G dash, and obviously the error correcting capability K, N, D, these properties are public. But what is kept private is the S, P and the decoding algorithm. So this delta is private, S and P are private. So here I have one way to show it in a block diagram. So it is G dash M plus E, which gives you the C. At the other end, first you perform P inverse, then the error correction algorithm, and then S inverse to get back the N. So a very small toy example, that very G matrix which we introduced for the Goppa code, and here we are giving one S matrix and a P matrix. So that by the pre-multiplication and post-multiplication you get to a G prime, which is also a 4-12 matrix, as you can see. Perform the M G prime, get to some message, and Y will be generated as Y M G P. This is the deliberate error, and then now you will be performing the P inverse and from decoding algorithm, and after applying the decoding algorithm, will be in the last step we will apply the S inverse and you will get back the message. So using the Goppa code and one S and P matrix, you are able to this example, this is a toy example, but it gives you, I think, some kind of a confidence building exercise that yes, it is something that should be working. A working example. So now I will just glance through what kind of attacks can happen. So there are two types of attack. One is the direct attack or message-wise attack. Another is the structural. So the message-wise attack means those multiple encryption problem, etc. So message-wise you are trying to get to it. The structural attack, you will try to guess now the S and P matrix. You got an access to the generator polynomial. So suppose, then you will try to guess the S and P matrix. So now what is the size of S, what is the size of P? And for like here, this is the size of S, 4 cross 4. So every element can have a value of 0 or 1. So 2 to the power 16 possibilities are there. There are 16 elements basically. So 2 to the power 16 possibilities are there. So you will try out all possibilities. You have a high performance computer through which all possibilities you just try to explore. So then there is some mathematics, and if you look at the of the permutations, how many permutations you have to perform, and then you see at the last one or two lines, you will see that to guess the right matrix, S to guess the right permutation matrix P. This is what a random guess can give you. So as you can see, it is very low. This is for a very large dimension, obviously, not for this one. And then if you want to discover the code words by getting to the closest, there is that at the minimum distance, which particular valid code word is available from what you have received. What you sent is deliberately noise introduced actually word, so which is the closest code word. So then again you can see that if you try to do an exhaustive code word comparison, so this is the total comparisons that you have to perform is huge. Then syndrome decoding. Syndrome decoding is basically what they do is they consider from the G star or G prime which we use, so which is in the public knowledge. They try to generate a corresponding parity check matrix and try to force a syndrome equation on that. So when they try to force a syndrome equation on that, they also get some kind of an error. And they claim that this G prime is also some other linear block code, and let us try to start the guess by using that particular linear block code. And then they apply the Gaussian elimination technique by solving for unknown S and P matrices from this particular syndrome. They try to generate all the possible error vectors and then try to guess. So that is one kind of attack. And in this attack, sometimes what happenings are guessed. They say that these K positions are free permission set decoding approach. So they say that these K positions are error free. Generator matrix and then assuming that these are error free, they fall for the remaining bits. And when they fall for the remaining bits, they have a lesser number of permutations to cover, and using this lesser number of permutations, sometimes they can get closer more easily. Multiple encryption problem, I have already explained what kind of problem is this. Now if you look at the last but one point, you will see that only after 12 trials the attacker will succeed. So this is a serious issue. Only 12 trials are needed to be successful here. So some of the critiques that were coming for this particular McAleese crypto system over the years is that encryption decryption speed is high, but multiple encryption is a trouble. Ciphertext messages are longer, key sizes are large, and the signature problem again for this. Although I have used a GOPA code so far, I have not explained how the signature can work. Now, one obvious thing is to get to a signature, a corresponding signature protocol as well. So, in coding theory, G and H, that is the generator matrix and the parity check matrix, in fact, the transpose of the parity check matrix, they share a duality, and that can be successfully exploited to get to a signature system. So that has been covered by Near Derator, who developed this particular crypto system where the starting point was the H matrix. As I said, the duality they can explore for designing the signature system. So the starting point becomes the H matrix. So they use the GOPA code H matrix, and then instead of the so they will be using one S and P, the pre-multiplying and post-multiplying matrix as usual, and then they will be multiplying this with the transpose of the message, and basically if you perform H into message transpose, so that basically gives you what is called the syndrome in the parlance of your coding theory. So they are basically now having a syndrome from where they which they set. So at the other end, a syndrome has been received, and so then the standard technique as was used for the message encryption, message decryption will be performed. So first the S inverse will be done, and after the S inverse is done, then you have a permuted H M transpose, and so from there you can get to you can retrieve back that particular message, which is basically nothing but that signature. So the fact that the syndrome decoding, regular decoding, they basically can be mapped to the same problem. So the regular decoder can perform the syndrome decoding here also, and from after doing that, the P inverse will be applied. So again, if you look at what is therefore the public information, it is nothing but the scrambled H prime and the plain text length and the error correcting capabilities. Private information is the S and P matrices, station and scrambling matrices, and the decoding. Again, toy example to build the confidence. So you have some H matrix already introduced for this Gopa code earlier. So some S and P has been introduced earlier also. So some H dash can be generated. So use this H dash to send the signature, which is M into H dash transpose, and then you introduce any kind of error, etc. At the other end, you try to decode it back. And so the message can be retrieved at the other end, either by using some polynomial or properties of matrices also may be used. Now we come to the last part. So what is the security issue we are facing today in terms of the post-quantum era? Yeah. So first of all, the signature system that we have introduced, it will also be subjected to some brute force attack, obviously. So all relevant entries can be exhaustively tried, and again that kind of permutation you have to see. You suppose you have access to the parity check matrix, then you can generate the syndrome, and you can try and guess from this error, you try and guess what is the nearest code word, because if you know the parity check matrix or the generator matrix, so you know all the valid code words. That is the big term. Then the attack would work similar to the earlier Macaulay crypto system attacks, and similarly there are other ways also to perform this attack. Like you can try to reduce also. Earlier we said k bits out of n are correct. From there we tried, and then here also you can try out t columns, because you know that t is the number of errors, and after all, when you multiply the h with n, you are getting t number of ones in the vector, in the resulting vector. That is the syndrome. So from there, obviously, you can make a better, easier guess. Information set decoding also is applicable. Basically, similar to what was applicable for the Macaulay crypto system, also applies here for the signature part of the crypto system. So a little bit of algebra and Gauss elimination, you can try and guess the solution, and you can basically reduce you can also show this problem can be reduced to the mutator problem, and then the everything that was applicable in the catalyst. Yeah. That is the basically the trouble that the coding theory has a duality between the G and H matrices. Both can also be considered as a generator matrix of another code, which is a dual of that code. So that those properties actually make this signature system, I could say, weaker than even the Macaulay super system to an extent. Not much improvement has been possible through the attack papers. They have not been able to achieve much improvement. Now coming to the post-quantum era, finally, you can see that the Macaulay system does not have the inherent properties which could be abused by Shor's algorithm. That's why Shor's algorithm could break the popular cryptographic systems, but not this one. Now, Prover's algorithm can be applied to speed, attain speed of the brute force attacks also. And for that, you would require instead of B bit security, you will require 2B bits of security to combat the speed that is going to be achieved by applying the Grover's algorithm. The brute force attack is so you have to increase the size of your key also. So if you look at this function, so basic T0 remaining the same, approximately 4 times bigger key sizes are enough. Find is to 4 times bigger key sizes would be able to tackle the situation in the post-quantum era. So this gives some kind of a guarantee that Macaulay's and neo-generator systems would survive in the post-quantum era. But same message trouble is still there. So in order to get rid of the same message trouble, what we basically can do is we can encapsulate the key that we are using. Even in RSA, we are doing the same thing. So some key encapsulation method, the idea is instead of sending the message, you encapsulate the message inside some random string, using some random string. So although you are sending the same message over and over again, actually you are encapsulating different random loops. So then the mathematical property vanishes. That is, just by looking at which places are same, which places are differing, you cannot get any idea about the message anymore. So that kind of an extra step of encapsulating into a random encapsulation of the message can solve this problem, as generally done in RSA also. Okay, so things keep going on in this arena of cryptography. So what looks like secure today can become redundant, and again looking redundant could come up with some protocols so that it again rises back as a secure system. So this keeps going on, and the idea of this Macaulay's crypto system is definitely not immune from this particular thing. Like, for example, generalized Reed-Solomon codes and Goppa codes, there is some similarity between them, and therefore from there a structural attack could be initiated by this Sidelnikov. They would break the neo-generator system. And then Gabidulin, he suggested one modification, and then again it survived back, and he showed that even with these modifications, much smaller codes can be used. So Again, some attack is now known for this particular system. So McAleese system advantage again. So as you can see that public key crypto system based on coding theory is still thriving and trying to compete in the post-quantum era. So finally, some of the references that I used for preparing this lecture, and number 5 is a specific one I have added, which I have not used in my lecture, but it gives you a review on how the control system communication are require the cryptography concepts and what kind of cryptography concepts are being used in therein. So a review paper has been added here in the bibliography. So that's about all I had to say. Thank you.
Thank you so much, sir. Anyone who is interested, having some question, don't think anyone is interested. We are very much short session now. Request our coordinator, Dr. Shibpur ma'am, to appreciate, give a short token of appreciation to our respected honorable speaker. Shutapa ma'am, are you there?
Yeah, honestly, thank you. Thank you very much, Dr. Abhik Mukherjee, Associate Professor, IIEST Shibpur, for his wonderful presentation. Coding theory, cryptography, really well-known areas of today's technology. Sir has given a very lucid explanation regarding this. Sir, your lecture is very helpful for our faculties, research scholars. Really, we are honored to have such an experienced people like you. We are enriched by your relevant topic. In this COVID-19 crisis, sir, we are in a virtual platform. We want to share a token of appreciation. I am requesting our very own Shushmita De, Assistant Professor of our department, to share the certificate of appreciation for our honorable speaker, Dr. Abhik Mukherjee. Shushmita, please share the certificate.
And all of you, please give a big hands to Abhik.
Round of applause. Yes, yes, for our Abhik sir. Thank you so much. Very much. Oh, it was name drop. Right, Shushmita. Shushmita presenting. Okay. Got disconnected probably, Shushmita. For net issues, I think. Can I share?
Yes, yes.
Yeah. Okay, she is again sharing.
Any one of you, please.
Okay, stop sharing. Okay. Stop sharing. Then what to do?
I think.
Okay, please. Okay, keep it time, please.
Shushmita.
Yes, sir.
Okay.
Just
Or else. Oh, okay.
Okay, I'm sharing.
Okay, Shushmita, let Orgo share, okay?
Okay, okay.
Orgo, please share.
Okay, I'm sharing.
There are some net issues are there. Just a minute.
Okay, please stop. I am sharing. Let me share.
Yes. Photography you
Right.
proceed.
That will be better.
Okay, sir, this is for you.
Not took enough application from our end.
Is it visible on the screen?
Yes, it is.
Okay, sir. Thank you, sir. Now stop sharing.
Yes. May I request all the participants present to please turn on your videos. We will have a short photograph session. Thank you, all of you. Tomorrow
Abhik
is
is there.
our last. Okay.
Abhik sir was there in the photograph. Just confirm
No,
that.
ma'am. It was not there.
Sudipta, Abhik sir is there.
Yes.
He
Abhik sir is
possibly
coming
wants
right
to
now.
take the photo.
He's online, but
Okay.
Yes.
he's
Sir
online.
is online now. Right. Right now you have to take the photograph.
Thank you, all of you. Tomorrow is our last day of the IIEST International Faculty Development Program, and tomorrow we will be having our session from 4 to 5. It will be delivered by Dr. founder and CEO of Azure Software Private Limited. So hope we will meet tomorrow sharp at 3:45 a.m. Thank you for today.
Thank you, Abhik for your nice presentation. Thank you.
Thank you all. Thank you all. Stay safe, all of you.
Thank you, sir. Thank you.
Thank you, sir. Thank you so much.
And the feedback link is already distributed on your WhatsApp group. The feedback link is already distributed on that WhatsApp group.
Okay. Goodbye.
I'll request.
Anything else? Yes, sorry.
I will request everyone to please leave the platform, and we will meet together tomorrow.
Yes.
So I will request everyone to leave the platform, and we will meet tomorrow.